Today we're going to talk about the sampling distributions and point estimation. When we're done, you should be able to answer questions like these. What is a sampling distribution? What's the standard error? What's the principle of maximum likelihood? What's bias in the statistical sense? What is a confidence interval? What's the central limit theorem? And why is the number 1.96 such a big deal? Here's a possible. We could roll a 1 on the first trial, and we could roll a 2. A 1 on the second trial. If we do that, the mean is 1. We could roll a 1 on the first trial and a 2 on the second trial. The mean is 1.5. We could roll a 1 and a 3. Our mean is 2. 1 and a 4, 2.5. 1 and a 5, 3. 1 and a 6, 3.5. Then on the first trial, we could roll a 2, and we could roll a 1 on the second trial, and we'd have a mean of 1.5. 2 and 2, 2 and 3. So here's the first roll of the die. Here's the second. So we're going to go 1 and then 1 through 6, 2 and then 1 through 6, 3, 1 through 6, 4, 1 through 6, 5, 1 through 6, 6, 1 through 6. And in each case, we've found the mean of those 2 throws or rolls of the dice. Now, I submit to you there are no other possibilities. So the sample space here is enumerated by these 1, 1, 1, 2, 3, 1, 5, 1, 6, 6. So we go from 1, 1 to 6, 6, and our means range from 1 to 6. So we can get 1 if we have 2 1s, and we can get 6 if we have 2 6s, and everything else is somewhere in between. And I have a graph here of, we just order these like so. You see that there's a nice orderly pattern that moves up as we go from 1 to 2 to 3 to 4 and so forth. Okay. So these are all our possible data, and I want to move to the next slide. There we go. This is what you would typically see for the sampling distribution of means. So now we've taken from the previous slide, you notice many of these are the same value. So this value is the same as this one, is the same as that, and so forth. So if we collect them together, there's one way to get a 1. There's 2 ways to get a 1.5. There's 3 ways to get a 2, and so forth. You can see the maximum value here is 3.5. I think there's 7 ways, 6 ways to get a mean of 3.5. So, and then there's 1 way to get a 6. So this is an interesting shape, isn't it? Look at that. So it's got a single peak in the middle. It's symmetrical. You know, if you roll a die, it goes 1, 2, 3, 4, 5, 6, which is a flat or rectangular distribution. And now when we're taking 2 of those and adding them together and dividing by 2, we get this nice shape of a distribution here. Okay, this is a sampling distribution because it's the distribution of means for every sample of size 2. So we figured out what could possibly happen. We listed every last stinking one of them, and then we've graphed it here. So this is the sampling distribution for a mean of 2 dice. Yeah, the mean of two rolls of the die. What's interesting about this is that the probability of finding one of these things, so the probability of finding a mean of 3.5 is bigger than the probability of finding a mean of 1. So if we just roll 2 dice, we're not going to get a 1 or a 6 very often. We're going to get a 3.5 with much greater frequency. Now, if you just add them together, of course, 3.5 times 2 is 7. So 7 is the most likely thing that you're going to get when you roll 2 dice, if you add them up. If you roll 2 dice and you add them up, you're rarely going to get a 2 or a 12. Right? 7 is going to be very, very relatively common. And if you understand this and you play games like backgammon, where you have to roll dice for things to happen, then you can use that to your advantage. All right. So notice that the probability of getting an outcome depends on the sample space. So there's lots of ways to get a 3.5 as a mean. And so the probability of getting 3.5 as a mean is going to be greater than a 1 or a 6. The sampling distribution shows the relation between the probability of a statistic and the statistic's value for all possible samples of size n drawn from a population. So in words, that's what I just showed you here. So here's the probability for all possible outcomes. And oftentimes in our kinds of data, we don't have, just 1, 2, 3, 4, 5, 6. We've got sort of a continuous underlying variable. So for example, height in inches. So when that's the case, you're going to, instead of having those that step function there, you're going to have a nice continuous curve like this. But in any case, the value of the thing, so we're doing a sampling distribution of means, we're going to have that along this axis, and the relative frequency or probability will be along the y-axis, the vertical axis. Then the more common, more frequent, more probable outcomes are typically here in the middle. All right, so that's the idea of a sampling distribution. Sampling distribution for the mean and the standard deviation. So you remember I said to you a little bit earlier, you could have a sampling distribution for the mean, the standard deviation, the variance, the range, the interquartile range. You can pick a statistic and have a sampling distribution for it. All that means is, you've got every possible sample of a certain sample size, and you plot them. That's your sampling distribution. It doesn't care. The idea of sampling distribution doesn't care if it's the mean or the standard deviation or whatever. But we work with the mean and the standard deviation all the time. So the sampling distributions for those statistics are particularly important. So that's what we're going to talk about here. The mean of the sampling distribution is defined the same way as any other distribution. That is, it's the expected value. So what's the expected value? That means the average. So the mean of a sampling distribution, you just find the sampling distribution, you take the average, that is the mean of that thing, that's the expected value. So for our dice example, for 2 dice at a time, that mean was 3.5. All right. The standard deviation of the sampling distribution is called the standard error. So that distribution here, this thing has a mean of 3.5 and it has a standard deviation of 1.25. So that standard deviation is the standard error, and that tells you the average distance of these means of sample size 2 from the grand mean for sample size 2. So what's the average distance here? It's 1.225. That's the standard error. This turns out to be useful in a lot of statistical applications. The variance of a sampling distribution is the expected value of the squared distance, a mean square. So that's where mean square comes from. It's a variance. All right. In symbols, the variance of g this is the expectation operator, is the expected value of g minus the mean of g squared. So remember, the expected value would be like the sum of this thing over n. So it's the variance. It's the sum of squares added up. The sum of squares is added up. The sum of squares divided by n. So take a break for a minute, hit the pause button, and ask yourself these questions, or find yourself a partner and ask these questions. What is a sampling distribution? What is the standard error of a statistic? So think about those things for a minute and come back, and if we were in class, we would discuss this, but can't do it. All right, so what is a sampling distribution? A sampling distribution is the distribution of the statistic over all possible samples of a given sample size. What is the standard error of a statistic? The standard error is the standard deviation of the sampling distribution.